Okay, so good morning, everyone. Welcome back. So it's good to see that we have about 60% of the class in. All right. So there's a few things. For the lab, I know a few of you all had some trouble getting the lab slot because it was uh, full. All right, and I've already asked them to increase the quota for the lab to accommodate all of you. Depending on whichever lab that you can fit into. All right. So if you still have any issues and you're not able to get the slot that you want, please do let me know. All right. And I will check back with the office to make sure that this is resolved soon. Okay. So that is the admin matter. Other than that, as what I mentioned, this week your labs will be starting. Okay, but this week's lab exercise is just to make sure that you collect your equipment as a project group, and at the same time your boards that you collect are working and functional. Okay, so that is the objective of this week's lab. All right, so let me get started first with the lecture slides on the software design basics. All right, and then we will talk about some of the labs and project along the way. All right, so in the last lecture, basically we had a introduction to the module, what we're going to be covering, all right, some basic recap of embedded systems design, okay, and just to give you started with the freedom board as well. Okay, so another important thing is in your Luminous, okay, if you look in the project under project folder, there are some data sheets there. Okay, one is the detailed data sheet for the microcontroller itself. The other is a data sheet specifically for the freedom board. Okay, so do download those data sheet and keep it with you at all times. Starting from the next chapter, which is on CPU onwards, we will be referencing that data sheet quite heavily. Okay, and I think that is an important document that you must have with you. All right, so you can download it later during the break time. Okay, you haven't done it so, or even done it yet. Okay, so let me get started with the software design basics over here. Okay, so in this set of slides, okay, so there are two halves to this. The first half is what we're going to cover. The second half, I've already put a note there. Those will not be covered, and it's only for your own reading. All right, and you can reference that just to get some idea. But I think those concepts will probably be covered in other modules as well. Okay, so what we want to do is we want to look at this idea of concurrency, okay, which is basically trying to make things happen at the right time. Okay, so when we say concurrency, generally we say many things happening at the same time, and that gives us the ability to think of things happening in parallel. All right, and how do we develop such code for embedded systems? So let's look at that in more detail. Now, in a microcontroller, okay, we saw this in the last set of slides as well. We say that a microcontroller is actually formed by putting together a processor with many other peripheral subsystems. Okay, so things like your analog block. Okay, for example, you want to do A to D conversion, D to A. You have timers. You have a serial interface. Okay, in other cases or in other controllers, you may have things like clocks, and clocks are there. Besides clocks, you also have watchdog, DMA. So some of these peripheral blocks you are familiar with. All right, you have probably seen it in either EPP 1 or 2 or in some other modules. At the same time, in EPP 2, we have also introduced you to the concept of interrupts. Okay, and through the concept of interrupts, we know that these peripheral systems, okay, these peripheral systems actually have a way of notifying us when certain events occur. Okay, so if you remember in EPP2, we used interrupts, okay, to trigger whenever the wheel sensor was rotating, okay, and at the same time for the PWM block and so on, we could use interrupt as a way to control the PWM or the timer and so on. Okay, so these are some of the concepts you have been introduced to in the past. Now, what we are seeing here is a system where you have software and hardware working together to achieve some level of real-time response. Okay, so you have a main program over here that will at the initial stage will probably do all the necessary configuration and settings for the peripheral subsystems. And after that, okay, once all your configuration is done up, you say you start timer. So when you say start timer, your timer peripheral block is configured to generate some periodic interrupts. Okay, so as you can see, these timer interrupts will happen at a periodic interval, depending on how you set up the peripheral block. And once the interrupt is triggered, you will jump to the ISR. Okay, so if you remember, basically, when you have your main code or any other code running, when you have an ISR triggered, you will momentarily pause whatever you are doing, jump to the ISR, finish up the ISR, and then return back, okay, and carry on. Okay. In this case, basically what is happening is in the ISR, you actually start the A to D conversion. All right. So in the A to D conversion, the hardware will generate is configured to generate 4 interrupts. All right, and every time you generate this interrupt, you jump to the ISR. Okay, so this ISR will probably take these values. Okay, so we don't know what's happening, but we can just say that maybe this is just taking the values. Okay, take the ADC values and probably storing it. Okay, and store it somewhere. Okay, in a buffer or in a shared global array or something like that. Okay, and once that is done, okay, you are updating some global flag that tells the main program that the ADC has completed. That means effectively 4 iterations of the ADC operation have completed, and you can start the next. Okay, so the whole idea of this kind of a design, which you are familiar with, is to allow your main program to use these blocks of time, okay, for other purposes. Correct. So each time I start the timer, I know that it will happen automatically by itself, and I can carry on doing other things. And I just when the ADC flag is set, then I know that these particular operations have completed, and then I can go and probably take this data and do some processing or something else. Okay, so the whole idea of having this kind of architecture is actually to provide some level of concurrency by maximizing the hardware capabilities of the microcontroller. Okay, so what you have done so far, what you have already learned so far, does achieve a good level of concurrency to get things done in real time. All right, so you're already capable of doing concurrent programming using this combined interface of hardware and software together. Okay, in terms of scheduling, all right, we know that there is no particular scheduling that we are currently doing. We are basically writing a simple loop. So you're inside your main program, generally what you have is you have a while one loop. Okay, so you probably have some initialization done first, okay, to configure your peripherals, your IO, everything, and then you may have a while one loop where you have some activities and you may wait for certain flags, and inside your initialization you already configured and set up all your interrupts. Okay, so whenever interrupts trigger, certain events are logged, certain data is captured, then you may process them inside the main loop. Okay, so definitely this is something we know and it works. All right, but there are of course certain drawbacks to this, all right, which we will be looking at in a while. All right, so this kind of approach is very good, very useful, and can get the job done in many simple cases. Okay, but once the complexity of your system goes up, then it becomes a lot more challenging, okay, to try and do come up with a framework that can still fulfill the requirements of the system. So as what is stated here is adequate for simple systems. So this is what we talked about just now. So when I'm in the process of doing something in my main loop, interrupt can be triggered. All right. So at that point of time, you may be in the midst of executing some code at the processor level. So you need to complete that first. Once you complete that, you can go ahead and do the context saving. So when you say context saving, you push some data on the stack, you save your register values and so on, and then you jump to the ISR. Okay, you jump to the ISR, and then you execute the ISR, and when you finish, you return or you restore the context. So this is where you restore the context, and then you are able to carry on from where you left off. Okay, so this is basically what is happening and what we know from the behavior of a main loop and a ISR code. And in this case, what we are doing is we are relying on the hardware interrupt system of the microcontroller. So if your microcontroller is able to generate interrupts for those peripheral blocks that we want, then it can really help us to achieve this kind of functionality. Now, the other alternative, if your hardware is not able to support this, is to use software to schedule this CPU time. Okay, so right now, what we have done is we have said, okay, we use the hardware interrupt mechanism of the controller, and as and when the hardware completes the activity, it triggers us, and then we can, we know what has happened, and then we can use that information to plan the next activity. All right, now if your hardware, or you do not want to use the hardware, or another approach would be to consider using software to schedule CPU time, and that is what we're going to be looking at first. So one is what we call static cyclic executive. This is what we already are using right now, which is to basically what we call the round robin approach. So in static cyclic executive, you do task A, followed by task B, followed by task C, and then so on, and then you go back and you repeat again. All right, that is your static cyclic executive or round robin. The other one is dynamic priority. That means when task A is running, you may have task B running after that, or you may choose to run task C or task D after task A is completed. So it may always keep changing. All right, the which task gets run next. Okay, so there is also variations to this in terms of whether you have preemption or you don't have preemption. Okay, so these are the things we're going to be discussing now. So let's have a look at this system that we discussed last week. So when I have a simple system like this, all right, it is basically a byte performance monitor. What we saw is you need to have a few different inputs. One is your wheel rotation, okay, to keep track of how fast you are cycling. All right, then you have some maybe some buttons which are not shown over here, so you need to capture the button press. Okay, then you may also want to display some timing over here, so you also need some clocking mechanism. All right, and since there is a display, so your output is a display over here. All right, so these are the basic things that you need for such a embedded device. Now, how would you go about designing this? Of course, if I give it to you as a project, each of you may have different ideas. So one possible way of doing it is I say that I settle everything in the interrupts. Okay, in a sense where upon reset, I just do all the configuration. So this is the basically setup. Okay, I configure all the parameters, the timers, the interrupts, everything is configured, and then I can put my device to sleep mode, okay, in my main, and as and when ISRs get triggered, I call the appropriate, or as and when the hardware gets triggered, I call the appropriate ISR to do something. All right, so whenever the wheel rotation sensor detects that the wheel is moving, I jump to this ISR and I perform the necessary calculations. Then I put the data in some shared buffer or shared variable, and then when I press the mode key or some other buttons, okay, then I activate this interrupt and do some activity. And to keep track of the time, I can have a timer that is running from the moment I reset my device. Okay, so this is just one idea only. You can of course have different ways of solving this or fulfilling the requirements of this device. And as you can see, looking at the device and looking at this requirement, you can very easily implement this code and get everything running with already the knowledge that you have right now, right? Using a Arduino microcontroller, okay, or any other equivalent microcontroller, you can write the code and it will work. Okay. Now, how about if we look at a slightly more complex application, something like this. So this is basically what we call a GPS-based pothole alarm system. This is used or is quite important in many countries. In Singapore, thankfully, we don't have much of a pothole problem because people like me pay road tax every 6 months, so the government has enough money to fill up all these potholes. Okay, so I think it's good, correct, that the roads are well maintained. Okay, so you don't have this issue to deal with, and you can drive freely. Okay, but in some countries there is the issue of this is still there. So you can have this as a possible application to warn drivers of upcoming potholes or any construction work or things that are happening that they should avoid. Okay, so if let's say now you're going to design this embedded device, okay, and you're going to put it in the car or in the taxi or whatever, so that they know that such pothole is coming up, in a few hundred meters. So what do you need to do? So in this case, you firstly need to sound an alarm. I guess you need to sound an alarm when you are approaching a pothole. Okay, so that the driver is aware. At the same time, you want to display your position as well as the pothole position on some map, okay, that the user can see. You may also want to log the driver's position information. So this could be useful, let's say if it's a taxi company or it's a delivery company, you want to keep track of where your vehicles are going. All right, so this may be a useful way of keeping track by making sure the information is logged. And for any embedded device, you definitely need to have some switches, some memory, and so on. So you also have all this hardware to deal with. Okay, so let's say this is the product you're going to build. How would you design the software? Okay, so if we go back to what we know, okay, we say that, okay, I have these functions, all right, so I can sort of break up this entire project into different functional blocks. So one is to say I want to decode. Okay, so whenever a new GPS data arrives, I must decode this GPS string that comes in and know my current position. And after that, once I know my current position, I need to do a check. Okay, so that I check my position across the database, and from there I will know whether any pothole is along the way. And of course, in our case, we also want to keep track of the vehicle's position. So we also need to record our position onto some memory. And we have switches where we need to monitor, okay, and also have LCD that you need to update. Okay, so for now, we have just assumed that we're going to use sort of polling approach to read the switches and LCD to also run at a periodic rate. Okay, then update of the LCD. Again, this is just to give us the idea of one possible way of implementing it so that we understand the challenges involved. Now, if I look at these tasks, all right, and I say I want to now schedule this in a typical, what you call, approach, how would we do it? So one way is we can use the cyclic executive or round robin approach. That means I do decode, check, record, switch, LCD, and so on. All right, so that is one way. So that is this approach over here, what we call the cyclic executive. So in a while one loop or endless loop, I go through one by one. Okay, once I finish, I go back and I start from the beginning again and again. Okay, and the challenge with this is the tasks will run at the same rate, correct? Because when I run a particular function like decode, the amount of time I take to run it the next time is always the same because I need to finish up everything and then I go back. Right, so the maximum delay is the sum of all task runtimes. Okay, so there's no way one of these functions will preempt another function. Okay, you always have to wait the same time to execute one more cycle of it. Now, that itself gives you the problem, correct, or the challenge. because if my GPS data is coming in real time, so we can't predict when it will come. So when new data arrives, when I just finish the uh, decode or checking function, okay, what will happen? Okay, so rightfully, if I go back here, I decode. If the GPS data comes just before the decode function, then no problem. All right, because the new GPS data will then be used for the decoding operation. Okay, but what if the decode or the GPS data comes right after I do the check? Okay, then I cannot use this new GPS data until I finish one full cycle. Correct, because record switch LCD, then the decode is finally using the new GPS data. And after the check is done, then only I will know if there is pothole anywhere nearby. Correct. So you can see there is now a huge time lag between when the new data has arrived to the time when I can actually use this new data to know whether there is a pothole that I'm approaching. All right, and this is quite significant, correct? Because if you look at it from a driving perspective, you can be driving at 70, 80, 90 kilometers per hour. Okay, so you need to have very real-time response to inform the user as quickly as possible. All right, so any delay could mean that the information is too late. Okay, so you want to avoid that. Now, the next, so since we see that this is a problem or a challenge, what can we do? So instead of static scheduling, we can now move to what we call dynamic scheduling. So in dynamic scheduling, what we are going to do is we're going to say that we don't always go in the same sequence. All right, we allow the sequence to jumble up depending on the importance of information that is available at each time. All right, so we schedule based on importance, or in other words, priority. All right, so this concept of priority now comes in. Who is more important, or what is more important? Okay, so the task that is more important should be able to run first and make use of the CPU, whereas the not so important ones can be pushed back a bit. Okay, and of course, in this, there is also some variation. One is called run to completion, or the other one is called preemptive. When you say run to completion means I finish my current task and then move to the next task. In preemptive nature, I will stop whatever I'm doing, regardless of whether I'm halfway through or not, and I will jump to the new task. So let's look at this over here. Now, if I look at it in terms of the dynamic run to completion, so this RTC is the run to completion. Now, if I would use the run to completion dynamic scheduling approach over here, and my GPS data arrives here. That means right after the record function has started, then what I will do, since I say run to completion, that means I will complete my record function. Okay, and after I complete my record function, your scheduler will have a priority table to know that since new GPS data has arrived, the decode function should be the highest priority function to run next. Okay, so immediately after record, I will switch over to the decode. Okay, so previously, as we saw over here, after record is actually switch and LCD. Okay, but because now we are dynamically changing the schedule, after record, I switch over to decode and then check. So as you can see right now, my response time has shortened. Okay, it has shortened by quite a bit. But it is still not as fast because you are still delayed by this record function. Okay, and this record function might take quite a long time, correct? Because you're talking about taking your information and logging to memory. Okay, and memory interface is always, in most cases, the bottleneck in the system. The memory interface is still quite slow. Okay, so this record function can slow down your entire response time quite a bit. Okay, so I will come back to this slide later. Now the other one is dynamic preemptive scheduling. In dynamic preemptive scheduling, the keyword here is preemptive. So when you say preemptive means you are able to stop whatever you're doing at any point of time and immediately switch over. All right, so you already started your record function over here. So here you started the record function, but your GPS data came in over here after I started the record function. Okay, so in this case, since it's preemptive, you will immediately say that decode is more important than record. So I will stop record wherever I am and switch over to the decode function and carry on with the decode function first, and then eventually do the check. And after the check is complete, then I can carry on with the record function from wherever I left off. Okay, so this is basically as you can see, the fastest response time you can get. Right, that means no matter what happens, the moment the highest priority task sort of gets triggered, correct? In this case, the trigger point is the arrival of the GPS data. The moment this new GPS data comes in, automatically your system knows that this the most important thing to do now is to decode this new GPS data and then perform the check before I carry on with anything else. All right, so this is definitely the best in terms of response time. Okay, so let me go back to this slide over here. So in this slide, what we are trying to do is we're just trying to give you a sneak preview of what is this idea of scheduling all about. So just now I mentioned that when a higher priority task or event comes in and triggers that there's another task that is more important, another function that is more important that needs to be run. So there must be somebody who is at a higher level managing all of this. All right, that means currently I have task 1 running. Okay, and maybe I have task 2, task 3, task 4 all here. All right, and when task 1 is running, suddenly the interrupt is triggered. Okay, the interrupt is triggered and something happens. Okay, like in this case, GPS data is triggered. Okay, it's updated. So somebody must be checking for all these events and all these trigger points to know that, okay, when this particular event has happened or this flag has been set, I should automatically change my execution flow so that instead of task 1 that is running, I should preempt task 1 and make task 3 go over to take over. Task 3 to take over and task 1 comes in and waits. Okay, because the task 3 is the one that is now more important because this event has happened. Okay, so now the tasks have this idea or have this new parameter associated with them known as the state of the task. Okay, the state of the task. So the state of the task will play a part in deciding who should run, and the person who decides who is supposed to run or who is supposed to wait, that person is basically what we call the scheduler. Okay, so these are concepts we will revisit in more detail when we start the OS part. Okay, but this is just to give you a heads up, okay, on how or what is going to happen. All right, so now we are now looking at functions or tasks, and we're saying that each task is actually having an idea of a state. So the state means I could be running. When I say I am running, a task is running means I am using the CPU. That means I'm actually executing code. I am performing something, some activity. All right. If I'm not running, I could be either waiting or I could be ready. If I'm waiting means I'm still in the queue. Okay, I'm still in the queue down here. Ready means the task that is now released to run. Now, when it's released and ready to run means you have already specified to the system that, okay, I am going to run this task next. Okay, depending on whether I'm using preemptive or run to completion, there is going to be a change in how this behaves. In run to completion, like what we saw here, when one task is running, so in this case record is running, So if a record is running and then the GPS data arrives, what happens? The decode task will then be put here. Okay, the decode task will automatically be put over here to say that now that is the next task that is going to be running the moment the record function completes. Okay, so this handling of this queue on who is next, all right, or who should take over the CPU, that is managed by the scheduler. All right, so this is the run to completion which we saw. Now in the preemptive approach, okay, that we just saw a while ago, if we look back at the, let me, okay, so let me just jump a few slides here. So in the preemptive, basically what is happening is you are now looking at the highest priority task. And the highest priority task will automatically get to run. Okay, so it is similar to just now what we saw, except that in the previous case, this arrow wasn't there. This arrow wasn't there. Why? Because when a task is running, it will run to completion and then you will go and join the queue. But in preemptive, when a task is running, it may not complete because somebody else more important might have come along. So instead of completing it, I will go to a ready state. That means I take a step back and let somebody more important come in and take over the CPU first. Okay, and then when that person has completed, then I will get a chance to run. All right, so that is the idea of, or the difference between run to completion and preemptive approach. Okay, this diagram that you see here between the different states and so on, this is just giving you a very simplistic view. There's actually more states that we will explore once we start the OS part. Okay, so let me come back to the slides here. Okay, so this is basically the comparison of the response time, okay, based on what we have seen. So the static is basically the round robin fixed schedule where there is absolutely no change at all. So you just go through one function after another function. There is no real-time switching of any of the sequence. In dynamic run to completion, okay, what is happening is you are able to dynamically say who should run next, but you still have to finish your current task. In the last dynamic preemptive, if you start something, you are able to at any point of time stop it, okay, and let the highest priority task take over and run first, and then you can switch back later on. Okay, so definitely this is the most ideal in terms of wanting a real-time response. Okay, so this ensures that the highest priority task or function is always given the CPU time that it needs to compute its activity. Okay, so these are the schedulers that we talked about just now. One is the Cyclic Executive. That one is nothing more than you yourself writing it in your code, all right, in sequence. Run to completion, and the last one is preemptive and dynamic. Run to completion is something that you can potentially implement on your own. All right, we will look at that in a while. Preemptive and dynamic is the one that is basically using the RTOS, okay, which is the objective of the course, and we will study it a bit later on. Okay, so if you want to have, like what we saw just now, something that is preemptive and very dynamic, okay, that means when something happens, I can immediately stop and change to the most highest priority task, and all of this is running in the background for me. Then you switch to an RTOS. Okay, if you want the run to completion based scheduling, it is something that is you can actually develop on your own. All right, so there's a lot of open source available. I'll just share with you some ideas later on. Okay, so the first one, Cyclic Executive. Again, we have it in sequence. The real-time capability, as what we saw, is given through the interrupt. So we have the foreground, background approach, where your interrupts give us this real-time response capability, and everything else runs in the background. Okay, so you can still have some real-time uh, sort of processing, okay, but your interrupts, as we have seen before in EPP2 as well, you should keep your interrupts very short and compact to do what is really important, and the backend processing of information and so on should be left to other tasks or other functions. Okay, because if you get stuck in interrupt for too long, then you will hold up your main loop. All right, so that also affects your dynamics of the system. Okay, so you want to keep your interrupt short and simple and leave the rest of the stuff to the background processing. The run to completion scheduler, what you can do is, if you want to implement on your own, you can create a sort of lookup table, okay, where you have to store some information, correct, on, for example, what is the periodic interval at which I run a task, when is the time I need to release the task, okay, and what is the state of the task, and so on. So it is possible to implement a run to completion scheduler on your own, okay, but you need to monitor the state of the task, when was the last time it was run, how much time it is going to take, and things like that. Okay, so again, there is quite a lot of things to consider if you want to implement something like this on your own. Okay, so the next alternative, which is better, is to go directly towards using a preemptive scheduler. And a preemptive scheduler is basically the bedrock of your RTOS. Okay, so when you use RTOS, you are already in making use of a framework that allows this preemptive scheduling. And more importantly is, preemptive scheduling brings a lot of other challenges as well, all right, in terms of race conditions, data integrity, how to make different tasks talk to each other, and so on. Okay, so all of this is already encompassed within the RTOS. Okay, so when you run your system on an RTOS, or you basically load your controller with the RTOS, you are not only having this capability of preemptive scheduling, you are also bringing together all the features that you need to make sure that you can develop a multi-threaded code while taking into account all these challenges that you will also have to face. Okay, so that is the idea of using RTOS. Okay, so this is what I mentioned just now. So I will not go into too much detail of the task state and scheduling, as long as you understand the idea that right now we are moving towards the idea that every task, every function has a state associated with it. All right, whether it is in the queue, is it the first in the queue, is it using the CPU, okay, is it currently being switched out because a higher priority task took over, and so on. So whenever different things happen, the state of a task will also change, and we need to keep track of it in the system. The good part is the RTOS does all of this for us. Okay, so when you use RTOS, RTOS, basically the state of the task, the switching, everything is handled by the OS itself. Your objective is to make use of this environment to develop efficient multi-threaded code. All right, so you must think of the OS as a toolbox. All right, a very well equipped toolbox with everything that you need. Okay, what you use with the tools and what you create with it is up to you. All right, so that is how you must look at the OS. Okay, so RTOS in general, it is the ability to guarantee the maximum response time for a system. Okay, the maximum response time. Now, this maximum response time again is tied to the real-time requirements of the system. And when you say real-time requirements, which means we're talking about deadlines. Okay, so as long as you're able to meet the deadlines, then you say that you are able to develop a real-time system. Okay, so what is inside the RTOS? Like I said, the key thing that right now we have been exposed to is the idea of a comprehensive task scheduler that is able to give us this ability to preempt a task to allow a higher priority task to run. Okay, so you can minimize the response time. Okay, and at the same time, you also have your interrupts that your microcontroller supports. But besides that, you have a lot of very important stuff, okay, which we'll be covering later. Things like inter-process communication and synchronization. How do I make different tasks talk to each other and synchronize? how do I manage the time? Okay, how fast or how much time a task will take. And besides that, you will also have, in most cases, a lot of additional features such as I/O, memories, file system, networking, GUI, and so on. Okay, so generally when you load an OS onto a controller platform, you will have a lot of other features that may also come together with it. You may choose to use it, or you may not include those libraries if you're not using them at this time. Okay, in terms of timing dependence, for a non-preemptive static, okay, basically every code runs to completion and then the next code in a very systematic order. Okay, so the amount of uh, time that you take is basically everything put together. But in a non-preemptive dynamic, basically what is happening is when task one is running, I will run to completion, but when I finish task one, I cannot say that I'll go to task two. All right. When I finish task one, I may jump to task five. Then I may jump to task six and task two and so on. So it is always dynamic. Okay, but it's non-preemptive. That means I will still run to completion and then I will switch to the next task that is given to me by the scheduler. In preemptive dynamic, okay, which is what we are seeing here, every task is running, but at the same time, I can get switched out and another higher priority task may run at any point of time. Okay, in terms of memory requirements, okay, for non-preemptive static and non-preemptive dynamic, what you see is the amount of memory that you need is consistent. Why? Because in either case, okay, you only have a situation where one task is running, okay, and when one task is running, it runs to completion. Correct, in both cases. That means when I say the task has run to completion, when it exits, okay, I'll say running to completion. Okay, when it exits the task, that means it can free up whatever stack that it was using, whatever memory that was allocated, it can free up and the next task can use that memory. All right, so it is the same amount of memory in both these cases. But in preemptive dynamic, what is happening is if task one is running, okay, and if task one, I've used up a certain amount of stack space, okay, and I've used up a certain amount of heap space, all right, because I've asked for some memory allocation and so on. Subsequently, before I finish, I may get preempted and task two might run. All right. So task two may also use some stack, may also use some heap and so on. And then I may get preempted and task three may run. Okay, so I need to have enough memory to cater to all the memory requirements of the different tasks that are in the system. Okay, so again, this is also handled nicely for us in the RTOS, because when in RTOS, when you create a task, you are also going to set aside a certain amount of stack space for that task. All right, so you will see that, okay, later on, probably when we start the OS part. All right, so that is basically what I wanted to cover for the first part, which is on giving you the idea and the motivation of why we want to go in this direction. All right, so this is important, okay, because we want to make sure that we know we already have some idea, correct, how to design embedded systems, how to create a foreground background system, okay. But now when your system gets more complex, all right, when you want real-time capability, how do you ensure that? All right, so for what we see, a system that is able to provide preemptive capability and dynamic scheduling is the one that is going to give us that real-time response. Okay, so that is what we're going to be focusing on. Now, this set of slides has a lot of other information from here onwards, which I'll not go through, and that is more on software engineering principles. Okay, so that is just for you to read, okay, or for you to look up when you're free. It is not tested, okay, and it's just for your own reading only. Okay, now before we go for a break, let me just do a quick poll now, just to give get your opinion on certain things, and then you go for a short break. Okay. Okay, so it's a question here. Hardware solutions like FPGAs are always better than microcontroller plus software solutions. Okay, so I think it's a very quick and simple poll, and let me just share the results. Okay, so I think unanimous answer is no, which is correct. All right, and basically FPGAs, some of you may have already maybe doing the module now, or may have done it in year one itself. FPGAs are of course very useful, very powerful as well. All right, and they can in many cases provide solutions that can be very efficient, okay, in terms of speed. All right, but it may always not necessarily be the best solution, okay, because when you talk about microcontroller for software solutions, now that we know that we have this tool called the RTOS, that RTOS can actually provide us with a lot of functionality and real-time capability that can match up with things that FPGAs can also do. Okay, so hardware solutions are of course very good. Okay, but basically FPGA is a device that FPGA says what? Field programmable gate array is basically an array of hardware blocks which you can configure based on writing your HDL, Verilog or VHDL code. Okay, and what happens is in FPGA, you are writing code that will be implemented or translated to hardware, correct? And that hardware, technically, in many cases, why it is able to perform very well is because you straight away deal with the data and process it immediately. In microcontroller solutions, what is happening is you are writing software that will be in the memory, and when the microcontroller boots up, what is it doing? It is going through the fetch, decode, execute cycle, correct? You fetch the code, you decode it, and you execute it. Okay, so take for example, I want to take audio stream, correct, and I want to process this audio data coming in real time, all right, and then I provide an output. If I were to implement it in a microcontroller or software approach, what will I need to do? I need to write software or have interrupts that can do A to D conversion, take this data, and then write the software to process this data, and then I output the result. If I were to try to solve this in FPGA, there is no fetching of code, decoding of code, nothing, all right? Because I will have a hardware block that can do the A to D operation, and once the A to D operation gives me the discrete samples, okay, I straight away pass it through another bunch of hardware blocks that will perform the processing that I need, and I can get the output straight away. Okay, so in many cases, FPGAs can be very powerful and can be very efficient for many dedicated solutions. The microcontroller plus software solutions, why they are good is because of the flexibility that you have. Okay, FPGA, once you decide and you design a particular sort of solution, when you want to make changes, you want to add on new stuff, it's a lot more work involved. Whereas for microcontroller, if now you use A to D, correct, and then later on you want to implement another D to A, or you want to use DMA, you want to use other peripheral blocks, everything is already inside the microcontroller. So it's just about writing the appropriate software to use those blocks. Okay, so they are both different sort of ways to implement and get things going. And of course, one of the advantages of microcontroller based solutions is if you're talking about mass producing or commercialization, whenever you want to do a upgrade on the field, it's easier to provide a firmware upgrade because you just need to refresh your memory and you have a new code. Whereas FPGA, to reprogram them is a lot more of a hassle. Okay, so it is still possible, but it's a lot more hassle. And the cost-wise, FPGAs putting them out directly on the market it's a huge cost. Okay, so that's why in most cases you don't have much products with FPGAs being shipped out. Okay, FPGAs are used to design a particular solution, like what I said just now, and after that you fix the solution and you just customize a IC chip based on that solution that you have. whereas microcontroller gives you that greater level of flexibility and upgradability later on. Okay, so these are just different ways in which you can design systems. And why I'm bringing all this to you all is, as computer engineers, all right, there can be many different pathways to a solution. Okay, and you don't necessarily always have to stick with one approach or the most advanced approach. In many cases, a very simple approach might be enough to solve the problem. Okay, so that is one thing I want to keep stressing. Okay, even at the end of this module, even though you learn RTOS and you see how powerful it is, do not think the RTOS should be the solution for all your embedded problems. All right. In many cases, your basic microcontroller with your simple loop and interrupts is more than enough. So use RTOS when you feel that that is the right solution or the right pathway towards the solution. Okay. So let's have a break now. So now it's now 10:55. Let's have a 10 minutes break and I'll see you back here at 11:05. Okay. And then we'll go through the next set of slides on the CPU. Okay. Thank you. Okay, so welcome back. Let's carry on with our next set of slides. So in this set of slides, we're going to be talking about the CPU core, just to have an understanding of how the ARM Cortex is configured. Okay, so many of this information here in the slides is again for understanding only. This more details on the processor core and assembly language programming and all this other stuff you will cover in other modules. All right. So in this module, I'm just giving you a brief overview so you understand what we are dealing with in terms of the CPU core, and then we will move on to other stuff. Okay, so before we get to the actual content, let's look at this picture here. All right, so in this, basically what is happening, and then this is important. Okay, I'll tell you why it's important. Okay, so you can see that there is a handphone being connected to a charging point. All right, so let's assume that, I mean, this is something that we do every day. Okay, and for some reason, let's say today or later when you try to do it, okay, it is not charging. Okay, you don't see the handphone charging. Now, what do you do? Okay, so I have launched a poll here with multiple responses. Okay, so you can select all that you think you will do when you have this condition here. Okay, that means you try to plug in, you connect up, and then it just doesn't work, right? It's not charging. Okay, and I'll tell you in a while why this is a very important question. So I can see that we have a few very rich people in our cohort who want to throw away the phone. Okay, so I think what 88% of you have voted. I think that's enough. 89. Okay, I will end the poll here. It doesn't matter you haven't voted yet. Okay, let me just share the results here. Okay, so of course 9 of you are very rich. Okay, so if you want to throw away the phone, please let me know. I can gladly accept it as a donation. All right, but again, I think those who say throw away the phone are probably just trying to be funny. Okay, nobody throws away the phone just because it's not charging. All right, so if it's not charging, what do? You try to troubleshoot and figure out what could be wrong. Correct. So in this case, there are only a few different factors that can affect this or can cause this. All right, your power socket, your cable, your wire, maybe you didn't plug it in all the way. Okay, the power point, the fuse blew, something. Correct. The last thing you will want to think is the phone is damaged. Correct. All right. I mean, that could be a possibility that the phone itself, that not the whole phone is damaged, but maybe the charging port, that particular charging port connection is loose or is damaged. All right, and then that could be the issue. All right, but we do not want to think that big at the beginning. We want to try to systematically troubleshoot to find out what went wrong. Okay, and in most cases, it is usually one of these other options, not the throw away the phone. Right, it usually is one of these other options. And this is the same mindset you should have when you are dealing with any embedded system device, okay, and you should have the mindset when you're doing the labs as well in this module. Okay, why I say that is because uh, in the labs, okay, I will be giving you in the lab manuals, okay, there will be some exercises where the code is already given, correct? But when the code is given, I will not necessarily give you the whole C file or the entire project file. I may give you a code snippet and say, okay, this is the code you need to get the GPIO to work or the PWM to work. All right, but I may not show you all the other stuff earlier configuration because we may have covered that in another lecture or another lab. Okay, and what students will usually do is instead of trying to look at it from all the angles of what is needed for this to run, they will just take that portion of the code that is given, they will compile and run, and they will not work, correct? And then when I go walk around the lab, they'll just tell me, oh, your code is not working. Then I say, okay, fine, it's not working, it's fine. Then what did you do to troubleshoot or find out? Then I say, nothing, I just compile, run, it's not working. All right, and that is definitely not an acceptable answer, correct? Not even for me and not even for you in the future when you go out to work, correct? You can't tell your boss, oh, you give me the board not working, everything not working, correct? The first thing I ask is, what do you mean it's not working? How did you conclude it's not working? What did you do to troubleshoot to find out what is the cause, correct? So that is the correct mindset you should have, uh, not only in this module, but in all the modules, especially in computer engineering, because you're dealing with both hardware and software. So things not working the very first time may be a common uh, thing, all right? The important thing is, okay, what could be issue? Is it the initialization, something was not done, you thought it was done, maybe the multiplexing was not done correctly, the power was not set up correctly, something else that was supposed to have been configured in the setup function was not done. Okay, you thought it was there, but it was not there, all right? And because of that, it's not working. Okay, so you need to check at the software side, you need to check at the hardware side, all right? You're driving your motors later on, you write the code, you run it, your motor is not spinning. Okay, the first thing I'll ask you is, have you confirmed that the PWM signal is in fact coming out of the pin? All right, and to do that, you must use your oscilloscope. All right, so these are things you have learned before in EPP1, EPP2, so you need to apply that knowledge here. Okay, so if the motor is not spinning, check the PWM first. Is the PWM signal actually coming out? If the PWM signal is in fact coming out, then you know your code is fine. Correct? Then the next step is, okay, the hardware side. Did my motor driver, did I connect up the circuit correctly? Have I applied the power correctly? Correct? So that is how you must approach and try to troubleshoot when you see issues. Okay, the TAs are there, all right, to guide you and help you along the way, but they can't just sit down with you for the full 2 hours to troubleshoot your issue. All right, they need to move around to all the groups. Okay, so in each lab session, you're talking about at least about 20 groups there. Okay, so they need to be able to move around and give advice to everybody. Okay, so they have the experience of going through this before, so whatever problems that you are going to see, they would have already seen it. Okay, which is a good thing, so they can probably give you the direction to look in the possible things that could have gone wrong. Okay, so take that advice and then try to resolve those issues. Okay, don't straight away say throw away the board or what. Okay, so now that we are done with that, let's move on to the overview of the processor. Okay, so we're just going to have a very quick overview, and I'm just going to again go through the data sheet, all right, uh, and I'm just going to briefly touch on a very simple concept on the GPIO, but you'll probably be doing the GPIO chapter next week only. Okay, but I just want to touch on it if we have the time. Okay, so again, come back to the fundamental microcontroller versus microprocessor. The processor is basically the core, all right, which is the ARM Cortex M0 Plus core. And again, it's always a good thing, correct, that we're moving in the direction of ARM. Not only has Apple shifted to ARM-based cores, there's also a lot of development of running Windows on ARM. There are already devices there that support Windows on ARM, and there's a lot more work being planned in that direction as well. All right. So as I mentioned in the first lecture, it is a very interesting. It has been a very interesting 2022 in terms of the processor war that has been going on, and I think it is going to develop further. Okay, so let's see where it goes. So it's definitely a good thing that you're learning ARM not in this module. I think in other modules as well, and that will definitely help to boost your profile. Okay, so the ARM Cortex M0 Plus core is the main processor core that is going to be running and executing your instructions. Of course, if you really want to know at the lowest level, then that will be another module where you learn assembly language processing. If you want to go deeper to the processor architecture, that is again another module, okay, on the processor or the microcontroller architecture. All right, but in this module, we are focusing a bit more on the higher level, okay, where we're going to run the RTOS on the processor core over here. Okay, and we at the same time, since the microcontroller, which is the KL25Z microcontroller, already has all these peripheral subsystems built in, your analog, your timers, your communication, we're going to tap on all of this to create our final project. So in terms of the M0 plus core, all right, basically what you have is your processor core here. Okay, so besides this processor core, you have other things. Again, we are not going to go into all. I'll just touch on a bit. One thing that we will come across later on is the NVIC. So NVIC is basically the nested vector interrupt controller. ARM processors make use of NVIC as a way to manage the interrupts for all the peripheral subsystems. Okay, so as we look here, okay, all these devices here, your analog, your timers, all of these can generate interrupts. So all of these will come in through here. Okay, and your NVIC controller takes all these signals and manages the flow of information towards the processor core. Okay, so that is the job of the NVIC. We will see that in a later chapter. Okay, another thing is this thing called the MPU, Memory Protection Unit. Okay, so this is something that you will see only in higher end processors like this. And what this memory protection unit does is it allows you to protect certain parts of the memory for restricted access. Okay, so in your design, there will be a memory map. Okay, so when you design a processor or a microcontroller, you have a memory map where you say that certain addresses are reserved for your flash storage, some for your RAM, some for your IO, and so on. And there are some of these memory regions you may want to protect. Okay, because you do not want somebody or some other application code to interfere with these memory regions. So you can actually specify that some memory regions. Okay, so you can say that, okay, from address A0000000 to A000FFFF. Okay, maybe these are some important is an important memory region reserved for my system, and I do not want anybody to accidentally touch anything over here. So in my memory protection unit MPU, I can say that this is only read access. Okay, so when I configure it this way, what happens is when any code maybe intentionally or accidentally tries to write to this address range, it will throw an exception. Okay, and then you can catch this exception and figure out what is the offending code and why is this happening. All right, so this is another feature of the processor. Debugging is something that is definitely very useful. Okay, previously for APP2, when we were using the Arduino IDE, okay, to write the code, we didn't have much of a debugging capabilities there. All right, at most what we did is we do serial print and we sort of capture those information to know what is happening. All right, but in so the Mega actually does have more advanced debug capabilities. Only thing is because we use the Arduino, the basic sketch interface platform, we were not able to fully utilize all of the debugging capabilities. All right, so in Cortex M0 Plus core, we also have this serial wire or JTAG debug port. Okay, so later I'll show you again the debug port that you need to connect to for this module. And when you use that together with the Keel IDE platform, you'll be able to do a lot of very good debugging. You can set breakpoints, you can check memory, you can check the registers. Okay, so you can really see what is happening while you are executing your code. Okay, so these are the main things that I wanted to touch on. Uh, Again, this load store architecture, again, this is basically about how the processor is designed. All right, and basically ARM is basically considered a RISC architecture. Okay, reduced instruction set computer. That means you have instructions that are very compact, and you do all the processing within the registers. All right, so you load data into registers, you process the data, and then you store the data back into memory. All right, so that is how this ARM architecture is generally designed. Okay, in generally register memory architecture, data processing can actually access memory or registers. Okay, but this is again not usually seen unless you have a different type of architecture. Okay, so generally for ARM, we say that we have a load store architecture where we load from memory, put to registers, and then we write back. In terms of ARM processor core, this is the number of registers you have, R0 to R12, the general purpose registers, you have stack pointer, you have link register, program counter, and so on. Okay, again, do not be worried about all of this. Okay, these are not tested or not examinable. Okay, this is just to give you some idea of the processor that we are dealing with. Okay, the details and all this assembly language programming with these registers you will cover in other modules. Okay, so that is not the focus of 2271. Okay, so in general, you have R0 to R12, general purpose registers for data processing. Then you have stack pointers. You have, again, stack pointer is basically to point to the stack whenever you jump to a function, you need to temporarily store data due to the processing of interrupts and so on. Okay, you also have a main stack pointer and process stack pointer, depending on what you want to use. Then whenever you are jumping to a function or subroutine, you need to store the return address, and that is stored in the link register R14. And your program counter is basically keeping track of the next instruction, the next address where to fetch the instruction from. Okay, so these are the general core registers inside your ARM processor. By default, when you power up, okay, you are in what we call thread mode. So in thread mode, by default, you are using the main stack pointer. Okay, that is in the single threaded application. Once you go to the OS, okay, so once you go to the OS or base environment, you switch to the process stack pointer. Okay, whenever there's an exception or an interrupt, then you switch to what you call the handler mode. Okay, so in handler mode, you are also executing code, but you are servicing a handler, or in other words, an interrupt. All right. In ARM documentation, you will also see this thing called privileged and unprivileged mode. Okay, privileged or unprivileged. Okay, so this again is about having the ability to do certain things or not. All right. So some processors, they can be operated in two different modes: privileged mode and unprivileged mode. And in privileged mode, what happens is basically you have the ability to do anything that you want. Okay, in unprivileged mode, you have restrictions, certain access. Okay, so imagine that if you take a handphone, for example, your Android or your iOS is the base OS on your device, but the app is a third-party application, correct? And you want the app to make use of certain resources that your phone has, but you do not want the app to do things that should not be done. So the app will run in what we call an unprivileged mode. That means you can do certain things, but you cannot do certain key things that can affect the integrity of the system. All right, so that is how you can relate privilege and unprivileged. That means you want full access or some limited access. In our case, this Cortex M0 Plus core is by default in privileged mode, so we have the ability to do whatever we need, okay, in terms of the programming and the configuration. There are also core registers to give you some information on the status. This will be used again at a very high level later on. So in terms of status, there are three things. One is, of course, your status of any execution. So any processor will always have this 4 flags or even more: negative, 0, carry, and overflow. So this gives you the result of any computation that has just completed. Okay, whether there was a negative answer, overflow, or anything like that. The interrupt PSR register, when you read it that way, you will know the exception number. So whenever there is an exception, okay, NBIT will store at the exception number. So from the exception number, you will know which interrupt triggered the system. Okay, and the last one is thumb mode or arm mode. Okay, this one I'll come to it in a while. Okay, so this program status register is actually a single register, but you can view it in 3 different ways. All right, later on when we look at some example code, we will see how to use this. To mask interrupts, there is a particular bit, and you can use it. And this exception mask register is basically the way in which you can use it to mask all exceptions or interrupts. All right, and if I want to use it, I have to use specific sort of special instructions. Okay, using the MSR and MRS instructions. Okay, so there are specific reserved instructions that are put in place if I want to write or read to this register. Okay, in terms of setting or selecting the stack pointer, privilege mode, and so on, there is also another register known as the control register. Okay, so for us, we will not be touching any of these registers, okay, because we will leave them as default. Okay, and when the OS is loaded, that default boot up code will already configure it in the correct setting for us. So we will not need to touch all of these registers, but this is just to let you know that these registers are there for us to use. Now this is the memory map of the Cortex M0 Plus, okay, and MCU. Okay, so in terms of the memory map, basically what they are telling us is, okay, so when the designers design a processor, okay, they will come up with a general memory map, okay, for interfacing different types of devices. Okay, so in this case, you can set aside, okay, 128 kilobyte of flash memory. Okay, that is the amount of memory that is available inside our KL25Z board. Okay, but the amount of space available, okay, for storing code, okay, is actually half a gig. Okay, so you can see that we are only using a portion of the amount of space available. Okay, so that is the difference between using the MCU, okay, the microcontroller, and using the actual processor core itself. So if you were to take this same processor core and you say you want to design your own microcontroller in the future, then you can actually add more flash memory to make full use of this entire space that you have. Okay, similarly for SRAM, okay, you are actually able to go up to half a gig of SRAM over here, and then from there you will be able to configure all the memory that you need. But in our case, we are only having 16 kilobyte of SRAM, all right, inside the KL25Z chip. Okay, peripherals like your GPIOs, timers, and so on, these are already mapped to this space over here. 4000 hex 4000 to 0x5FFF. Okay, so this is the entire space set aside for all your peripheral systems. So when you say peripheral systems, you are talking about things like your GPIOs, your timers, ADCs, and so on. Okay, so I will not go through all of this, but the idea of a memory map is telling you that certain devices have to be already mapped to certain addresses. Okay, at the same time, you also have free space available for external connections. If you see down here, I have some space here set aside for external RAM and for external devices. Okay, so if I want external peripheral devices mapped to my processor, I have this address range to map to. Okay, now how do I do mapping using addresses. Okay, so that is actually a different topic altogether, and I will actually be talking about that towards the end of the module. Okay, how do you design address mapping hardware? Okay, but for now we will take it that the hardware is already mapped for us with specific addresses on the KL2YZ port, and we will use the mapping that is given to us. Okay, so for now we don't need to worry about any of these specific addresses over here. All right, but we will be looking at some of these addresses later on as we look at the peripheral subsystems. Okay, just to understand and relate back to this memory map. Okay, so you can see how it is all linked together. Okay, the next one is Indianness. All right. So this thing is something that is important. Little Indian, big Indian. All right. So this Indianness basically tells us the order in which a multi-byte value is stored in memory. All right. So if I were to take a 4-byte value, okay. So 1, 2, 3, 4, 5, 6, 7, 8, and I say this is address A. Okay, and this is A plus 1, this is A plus 2, this is A plus 3. Okay, and I say that this is the information stored in the memory. All right, if I were to say that now this system is a little Indian system. Okay, in a little Indian system, the least significant byte is stored in the lowest address. Okay, the least significant byte is stored in the lowest address. So if I see A plus 1, A plus 2, A plus 3, so this is the lowest address. Okay, and this is the highest address. Okay, so in terms of little Indian format, all right, this data would be interpreted. Okay, so assuming that everything here is okay. Okay, that doesn't matter whether it's decimal or hexadecimal, we will just take it as the values. So since this is a 32-bit value, I can say that in little Indian it will be interpreted as 1, 2, 3, 4, 5, 6, and 7, 8. In big Indian notation, the most significant byte is stored in the lowest address. Okay, so the most significant byte is here. So it's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so why is this important? Because when you store multi-byte data, all right, you need to know how it is stored. Because when that multi-byte data, if you read it as that same multi-byte data, that means, for example, I store one word. Okay, so if I, for example, create an integer x and I say that x has a value of something, all right, 0x. Okay, so this value, okay, this 4-byte value, for example, is stored in memory. But if let's say now I go to the memory location and I say I want to read byte by byte. Okay, so instead of taking it as one full 32-bit or 4-byte value, I now want to extract out a particular byte. Then I need to know which address to go to. Correct. So that is where this understanding of Indianness comes in. So you need to know exactly which address that particular byte is going to be stored in. All right. So that is where this concept comes in. Okay. So again, we will see that later on once the programming starts. In Cortex M0 Plus is based on the ARM V6 architecture, which is Little Indian. So for us, we just take it all to be Little Indian. All right, your code as well as your data, everything to be Little Indian. So there's no confusion. In some cases, you may have a mix of Little Indian and Big Indian between code and data, which can cause some confusion. All right, the last part here is on thumb and thumb 2 and ARM instructions. So basically, this is just to give you an idea that, okay, when ARM started many years back, the whole idea was to design very optimized 32-bit architectures, okay, for computing systems. All right, and so even though ARM started out with 32-bit, again, when you say that your processor is 32-bit, okay, it means what? It means that all the registers, okay, all the registers R0, R1, everything that you're dealing with is 32-bit. Your internal registers are all 32-bit and so on. Okay, now when your processor is 32-bit, Okay, it also makes sense that your memory that you interface with, okay, your memory and your micro P, that is also 32-bit. Okay, why? Then it's easy for you to do a single read and a single write directly in 32 bits. Okay, if your memory is 16 bits or some other value, then definitely it is still possible, but it is a lot more work involved. All right, that means I need to do read 2 times, I need to write 2 times, and so on. Okay, so definitely if everything is the same, then it is easier for interfacing. Okay, so in the past, because memory had not caught up in terms of pricing, 16-bit memories at that time were cheaper than 32-bit memory. All right, they decided to design a slightly modified architecture to fit 16-bit memory systems. So that's why they came up with the thumb instruction set, okay, where they have 16-bit instructions instead of 32-bit. Okay, and of course, then again, uh, memory price started to drop and it became a bit more affordable to support 32-bit memory. All right, and what they did is they cannot just dump 16-bit, correct, and switch to 32-bit. So that's why they came up with this architecture called thumb 2, where you support both 16 and 32 together. And the whole idea is so that people who had already switched to 16-bit, they could still carry on using the same code base and still run it using the new architecture that supported thumb 2 instructions. So that is a bit of history behind why we have 32-bit instruction and 16-bit instructions for ARM processors. Okay, but in our case, we are again not looking at it at that such lower level. We are still going to programming in C. Okay, so the compiler will deal all of these issues for us. Correct. We just need to be able to make sure that we are able to program correctly in C. Then everything else is done by the compiler. Again, instruction set is again more specific towards the understanding of low-level assembly language programming. So when you are specifically programming in Thumb or ARM, then there are certain things you need to be careful about. But again, I will not go through this because that is only when you're doing assembly language programming. Okay, so that's all I have. So before we end, there's two things that I want to talk about. So the first thing is this, all right? Like I mentioned, your board is quite sensitive, and if you do not handle it carefully, components drop on it, things drop on it, and things like that, it can easily damage the board. Okay, so one possible idea, actually, in fact, last semester also I asked the students to do this, but the problem was because of the zoning, they were not able to make use of the makerspace at SOC to do the 3D printing. Okay, but now all of us have access to that. So if possible, I know from the last batch of students that there are already 3D print models available for the KL25Z board. Okay, or you can design on your own, where you can encase it safely with just the header pins and the USB connectors coming out and so on. All right, so you can design something, or if you find something, you can share with the rest of the class. All right, and all of you can 3D print a casing for your board. All right, again, that is for your own good so that you protect your board. Don't leave the controller and all the circuitry exposed, and you just let the connections and the connector points to be exposed. Okay, so that is the part that I hope you all can do if you have the time. If you do find resources and you want to share with the rest of the class, you can send to me. I can put it up on the forum, or I can send an announcement to everybody. Okay, so that we can all get this done. Okay, so before we end, there's just two things. So let me just first stop this share. Okay, so in terms of the board, okay, so this is the board. Again, what I want to show you is when you collect your board this Friday, okay, you do not need to solder these header pins all yet. We will give you the header pins, but you do not need to do any soldering. Make sure you take out the board and you test it first. And do not touch, okay, do not touch the surface, either the front or the back, with your bare hands. Okay, just hold it by the sides over here. Okay, in terms of connections, I've already explained in the handout. Okay, the connection that you need to use is this one over here, the open SDA. So this is the one that is actually the debug interface. All right, so this debug interface will help us to make sure that we are able to do the debugging effectively using the Keel IDE software. So before when you come to lab this Friday, make sure that you already install the Keel IDE, all right, and your PC side, everything is set. Okay, and this Friday when you come to the lab, okay, what will happen is you will be issued, okay, as a group, what will happen is one person in each project group will be signing out one Ziploc bag, okay, with all the components inside. So we will give you a checklist, and you need to go through that checklist to just see what is there, what is not there. Uh, all these small items, LEDs, drivers, and so on, anything that is damaged, no problem. Okay, if because you can't test them right now when you collect it. Okay, so along the way when you are building up your robot, you say that your motor driver is spoiled or something is damaged. Okay, I can do a one-to-one exchange with you, no problem. Okay, the only thing that I have very limited and very strict amount of quantity is the freedom board. Okay, so that is the only thing where each of you is given one, so you need to take care of it very carefully. All right, so on Friday your objective is to go through the lab 1 manual just to make sure that it is working. Okay, by default once you plug it in, you have the RGB LED taking effect, okay, as you tilt the board, and then you just need to go through the steps in the lab 1 manual to make sure that you can now download and run a code using the Keel IDE software. Once that is done, then you are free to go. If you want to stay back in the lab to do any form of soldering, that is fine. Okay, you are free to do it. But again, like I said, don't use the board as your test bed. Okay, if you want to practice your soldering, you want to improve on it first, you can ask Uncle Jalil for some spare boards and take some resistors or so on, and then practice your soldering or wires. Okay, only when you're confident, okay, you do it. If you are still very unsure of yourself, ask your friend to do it. Okay, so for this Friday, that is the objective. Okay, making sure that is done. Then next week onwards, your tutorials will start, and I will also be uploading the weekly labs. Okay, as I mentioned in my first announcement, the labs will be optional. Okay, only this first lab is compulsory because I need you all to come down and individually sign out the boards. Okay, other than that, the subsequent labs will be optional except for two labs. One is the mid review lab, so there'll be a one lab session in either the week before the recess week or the week after the recess week, where I will do a sort of mid-semester review for you all to demonstrate certain functionalities. Okay, and the reason why that is important is I don't want everybody to just leave everything to the last 2 weeks. Okay, and then suddenly nothing is working. Right, so at least this mid-semester review forces you to fulfill the basic device drivers, your LEDs, your motors, all those stuff will be working. Then the last one will be your final presentation. Okay, so these are the two main things that I will need you all to come into the lab for. Other than that, if you do not wish to come to the lab but you want to work on your own, is fine. But the advantage of coming to the lab is you have all the facilities there, your multimeters, your power supply, your scope, everything is there. So if things are not working, it's easy to troubleshoot and find out what went wrong. Okay, so that is the main advantage. So as much as possible, if you can come, please do come to the lab. Okay, other than that, that's all I have. So this Friday, the TAs will be there to oversee the handing over of this equipment. All right, and like I said, all the TAs are the ones who just completed this module, either the most recent semester or one semester before that, so they know exactly what is going on. So they'll be able to give you the correct guidance. So no need to worry, you all are in good hands. Okay, so any questions you all can ask me. Okay, so for the team, those who have filled up the Google form regarding they are unable to find a team, I will allocate you all to a team by end of today. And those of you who have only 2-member teams, all right, I will see first. What I will do is I'll try to group together those who currently don't have a team. If there are still 1 or 2 that I cannot allocate, then I will put them into maybe some of the 2-member teams. Okay, if any of you are currently having 2-member teams and you want a 3rd member, let me know. Okay, if you want a 3rd member, I will gladly allocate you a 3rd member. If not, I will group the rest of the students first, and then those who still cannot be grouped, I'll put them to 2-member teams. Okay. Yeah, so that's all I have. Those who don't have a group, don't worry. I will allocate you all to groups by the end of today. Okay, so that's all I have. Thank you very much. Okay, and I will and see you all in the lab. Okay, this Friday.